We're here to talk about a topic that's something the two of us are incredibly passionate about. It's something that we spend most of our days thinking about. Pretty sure Niall dreams about it most nights. It's a topic that's especially timely today, and that is Snowflake optimization. So my name's Ian, and this is Niall. We are the founders of a company called Select. We provide software that helps users lower their Snowflake spend and optimize their usage. Through doing this, we've worked with nearly 30 different companies using Snowflake in a variety of different ways. And today we're really excited to share all the different things we've learned through that process and things we wish we knew when we were starting out a few years ago. Before we kick things off, we want to set some context. So last year marked the end of the longest bull run in history. And that was a period where companies were really focused on growth and maybe less concerned with how much it was costing to achieve that growth. If we flash forward to today, that has flipped, and now most teams or departments within companies are being asked to more carefully scrutinize their spend and potentially lower that spend. If we look at the data team, after human costs, the biggest cost center is typically the data warehouse. So that'll drive most of their SaaS spend. So what we have now is data teams that are being asked to more carefully monitor, understand, and lower the spend within their warehouse, and correspondingly try and write more performant SQL. So today's talk will focus solely on Snowflake. Snowflake is a market leader in the data cloud space, and they have lots of different cost and performance levers available, which we believe allows you to run one of the most cost-effective data warehouses. With that said, if you're not using Snowflake, a lot of the principles we'll talk about today will apply to most of the modern data warehouses that are out there. Snowflake optimization is a long topic, and Scott respectfully declined our request to give a 4-hour lecture, so we're going to do the best we can in the next 30 minutes or so. I think we'll have a couple minutes at the end for questions, but I do want to call out that there is an official office hours. So we'll be there immediately after this talk if people want to go deeper into any of the things that we discussed. I also want to mention that we will post our slides that we use for this talk on our website probably later today. So don't worry about if you miss anything. We're going to be posting links and code snippets throughout. So those will all be available online later. And then, lastly, we're both going to be here until Friday. So if you want to chat with us about any of this stuff at any point, I think we plan to wear these t-shirts every day. We have some extras, don't worry, it won't be too smelly. All right. So before we dive into the different optimization strategies, we'll do a quick overview of Snowflake's architecture. The one thing I do want to call out is Snowflake is more than a data warehouse. It's a full-on data cloud. But today we're just focusing on the data warehousing core product that most customers use. So, Snowflake's architecture. A big part of Snowflake's popularity came from the fact that they have these 3 different layers, each of which scale independently. So that first layer is cloud services. So this will be the entry point for every interaction you have with Snowflake. It will do things like check authentication and access control for the data. It does a very important step called query optimization, where it actually figures out what data does your query need to access and what's the best way to perform that query. We're going to talk a lot about that. And it does other things like transaction and infrastructure management and has a giant global result cache, which is great for performance. The second layer is compute. So this is where the actual query execution happens. And Snowflake has this interesting concept of virtual warehouses, which we'll spend a lot of time on today. What they allow customers to do is create different warehouses or compute clusters that can handle different workloads or different use cases, and customers can have those warehouses or configure those warehouses with different settings based on their needs. The final layer is storage. So Snowflake runs on different cloud providers. Depending on what cloud provider you use, your tables will be stored in the storage service from that cloud. So for an example, if you're using Amazon, your tables would be stored in Amazon's S3 service. To tie all this together, it's helpful to study the lifecycle of a query in Snowflake. So if we look at the top left, you have an analyst that's way too excited who's about to submit a query to Snowflake. So as mentioned, as soon as that query gets submitted, the first entry point is cloud services. So after cloud services checks Are they authenticated? Do they have the right access to access these tables? It would then check the result cache. So the cloud services layer has a result cache where it stores the results of previously executed queries. So if they're the same, it doesn't need to repeat all that query execution. It can really quickly fetch that result, which is great. For this example, we'll pretend that this query hasn't been executed before, so it has to skip the result cache, go on to things like query optimization, check for other conflicting transactions, and decide which warehouse to run on. That brings us to the compute layer. So in the compute layer, the servers will read from remote storage, so they'll fetch the data they need to produce the results of your query, perform all those computations, and then return those back to cloud services to store and back to the client. From a cost standpoint, what we typically see with the customers we work with is that this compute layer makes up typically about 90% of what people will spend in Snowflake. So that's really where we want to focus most of our time today. There are things you can do as well to reduce your spend or optimize usage on the storage and cloud services layer, but we're really going to focus heavily on the compute side. If you want to chat about those other ones, let's connect after. All right, I'm now going to turn it over to Niall, who's going to talk about best practices when it comes to setting up your virtual warehouses.
Great. Okay, so the first thing that we need to understand is Snowflake's billing model. And then once we've done that, we're going to talk through optimal virtual warehouse configuration, and then also the importance of warehouse consolidation as well. So Snowflake uses usage-based pricing, which means that you're only paying for the resources which are active at any given time. And it also uses per-second billing. Snowflake has a currency called credits, which are between $2 and $4, depending on your Snowflake edition. And each warehouse size consumes a different number of credits per hour. So the smallest warehouse in Snowflake is the extra small. That's 1 credit per hour. The small is 2, and so on. And there's a minimum of 60 seconds billed each time a warehouse is resumed. So what's a virtual warehouse? A virtual warehouse is an abstraction over the compute instances that your Snowflake account is running on top of. So for AWS, that's EC2. For Google Cloud Platform, that's Compute Engine. Each node that forms a virtual warehouse is roughly kind of 8 cores or threads, 16 gigabytes of RAM, and it has a local SSD as well. The exact specs vary between cloud platform, but that's the rough kind of level. Snowflake uses these t-shirt sizes to designate the resources available to each warehouse size, and they go all the way from an extra small to a 6XL. And each size represents double the resources available, but also double the cost as well. And increasing the warehouse size is called scaling up. So that means that the query has more and more resources available to run on top of, which should give it more performance. We also have something called multi-cluster warehouses. And these are available in Enterprise Snowflake editions and above. And these really are best used for increased query volumes. So not necessarily more complex queries or larger data volumes, but just where the number of queries increases throughout the day, multi-cluster warehouses can be used to meet that demand in a cost-effective way. And Snowflake will also scale those instances in when they're no longer being used. So here's how we recommend that you configure virtual warehouses. It's always good to start with the cheapest option, which is an extra small and single cluster warehouse. There's a setting called the max cluster count, which shows how many clusters Snowflake can spin up to maximum to meet that load. And whenever you see queuing, you can increase that max cluster count to allow Snowflake to scale up to meet that demand. There's also a setting called auto suspend. And so this is used so that Snowflake measures how long it's been since a query was running, and once it exceeds this threshold, Snowflake will automatically suspend the warehouse. So by default, Snowflake actually sets this to 10 minutes for any warehouses that you create through the UI. We recommend setting it to 60 seconds, pretty much always. And that's going to give you a really good balance of efficiency and cost as well. The next thing that we recommend changing from the default is the query timeout. So by default, Snowflake will cancel queries after 2 days of execution. But most of the time, if a query is running that long, it probably should be. So we recommend reducing that to between kind of 2 or 4 hours. Obviously, that will vary on the warehouse, the virtual warehouse that you're using, because some kind of transformation workloads, maybe they take longer, but equally, BI queries should probably take a lot less time. And finally, we recommend using resource monitors. So resource monitors are a relatively new Snowflake feature in the last year, which allow you to be alerted either when your usage exceeds a certain threshold, or you can set an alert based on exceeding like a rolling average of the past few days, which is a great way of being alerted on usage spikes without having to say what anomalous usage is. And when it comes to warehouse sizing, it's really important to set that based on the workload that's running on the warehouse. So for workloads which can tolerate some queuing, for example, data loading or transformation, anything which isn't user-facing, the best way to configure that warehouse is to have some queuing, which seems counterintuitive, but what it means is that the warehouse is being really well utilized. So whenever the warehouse is being billed for, it's always being used at full capacity. When it comes to data transformation workloads, I'll give an example for dbt, but this applies to other tools as well. Rather than increasing the warehouse size for every single transformation when it gets too slow, actually, if you just find the kind of slowest couple of workloads within that transformation process and just put those on a larger warehouse, you'll get way more cost-effective utilization. Because some queries just don't scale that well on a bigger warehouse, which I'll show next. So by just putting those slower, more complex queries on that bigger warehouse, you'll get much faster runtimes at the best possible cost. So this is how we like to kind of visualize the effect of warehouse size on query execution time. Most queries will perform great on an extra small. So this is really just for kind of those big data transformation queries that you run. And what you'll see is that queries improve in speed roughly double as the warehouse size increases up to a certain point. And that's because queries can distribute well across more resources, so more CPU, more RAM that we mentioned before, up to a certain point at which Snowflake will just go, actually, this query can't run any faster across any more cores. Like, it can't be parallelized any better. At which point, the query speed is going to remain the same, but the cost is going to go up, right, because the warehouse size is even bigger. And so the best way to find this sweet spot is to increase the warehouse size once at a time, observe the query time halve, and then once you see that starting to tail off, actually just go back down one warehouse size, and that's going to give you really good cost and performance. Okay, and the final thing on this warehouse configuration section is consolidation. So something that we see quite a lot is organizations who have a lot of virtual warehouses. And it makes sense because Snowflake bills per warehouse, as I mentioned before, and actually in the Snowflake UI, that's how you can visualize costs at this per warehouse level. So to understand costs by team, by project, it's a good place to start. The downside of using so many warehouses is that you end up with much less efficient usage of that resource. So as I mentioned before, Snowflake always charges you for the first 60 seconds of a warehouse running. And if you have lots of warehouses which maybe only process a query every 30 seconds or a few minutes, you can end up paying for a lot of completely unused warehouse active time. So instead, we recommend creating warehouses by workload requirements, so not by domain. So for example, we've got on the bottom here, kind of dbt, we've got a warehouse for each size, which maybe the models are configured individually to run on. And then we have some observability tools, which are also all sharing the same warehouse because they have the same kind of requirements. And likewise, maybe we have a user-facing warehouse where we need to make sure that there's no queuing, the queries are really fast. That can all go on one warehouse. The downside of this approach is that we've lost this immediate granularity of usage observation that you can get in Snowflake's UI. But we'll talk a little bit later about a package that we've made which uses query cost attribution, which then allows you to roll up costs by any dimension that you care about. So maybe that's by user or by something else. So even though you've got these consolidated warehouses, you can still get really granular cost reporting, even more so than at the warehouse level. Okay, let's move on to optimizing performance. And to start with, we're going to talk through pruning and clustering, and then Ian's going to talk a bit about query design. But pruning and clustering are really important to understand first. So there are three topics I want to go through. The first is micro-partitions, which is Snowflake's table format. Next is pruning, and then finally the thing that enables pruning, which is clustering. So Snowflake uses its own proprietary closed source file format, which is called a micro-partition. And these are just stored in the cloud provider that your Snowflake account runs on again. It's what's called a hybrid columnar format, which means that each contains batches of rows, so the Snowflake can only retrieve the micro-partitions that are relevant to the query that you're running. But also, within each micro-partition, Snowflake can retrieve just the columns that you're selecting as well. And that's really just all about reducing the amount of data which has to be scanned from remote storage, which is a really costly operation in computing. The other thing worth knowing is that micro-partitions are immutable. So they can't be edited once they've been created. Instead, Snowflake has to delete and recreate them. And that's why Snowflake recommends against lots and lots of small DML operations in a table. So it's good to avoid doing lots and lots of inserts and lots of updates. And instead, you want to kind of batch those together to get the best performance and cost. Snowflake records metadata for micro-partitions. And the most important one to understand for the next topic, which is pruning, is this minimum and maximum value that Snowflake records for each column. And this is how it can discard micro-partitions which it knows aren't relevant to the query. And this metadata is stored in the cloud services layer that Ian mentioned earlier. And so it means that it's available to Snowflake before it even starts processing your query. Snowflake can identify which micro-partitions are needed. So pruning, this really is the secret to every fast query success. We've got an example query here, which is selecting from this orders table for all records after August 2022. And we can see here in this kind of illustration, there are 3 rows per micro-partition. In reality, there will be tens of thousands, if not hundreds of thousands per micro-partition. But in this example, we can see that in this created at column, each micro-partition has only got a very narrow range of values for that created at column. And because Snowflake has stored the minimum and maximum value in its metadata layer, when it sees this query and that we only want records after this date, it can immediately just discard most of the micro-partitions in the table because it knows that they're just not relevant to answering the query. And you can identify pruning using Snowflake's query profile. So on the right-hand side here, in this little window at the bottom, we've got 2 stats which are important to know. So the first is partitions scanned, and the second is partitions total. Partitions total represents the total number of micro-partitions which are used by tables that you've queried from, and partitions scanned is the ones that have actually been retrieved. So we want that partition scan number to be as low as possible, and wherever that scan number is really high, that shows that we're not getting good pruning performance, which usually shows that there's an opportunity to do some optimization. So before we saw this orders table, which has got a really narrow range of created at values between each micro-partition, and this is called clustering, right? So clustering describes the distribution of data across a table's micro-partitions. And a column is described to be well clustered when we have that state, so only a really narrow range of values per micro-partition. And as a result, Snowflake can prune really well when we apply a filter on that column. So how do we get into this well-clustered state? There are kind of 3 ways that we like to categorize these. The first is natural clustering. This is by far the best because you don't have to do anything. And this occurs just because records are naturally inserted into a table with a column which represents when they're loaded. So for example, with the orders table again, as new orders are generated and ETL'd into that table, we get new micro-partitions that are created, which have all got really new created at values, which have all got a really tight range. And that's great because if we query based on a created at column, we're going to get really good pruning performance without doing anything. But sometimes the natural order of the columns, the natural order of the insertion doesn't actually match the usage pattern. So let's say we have a few teams who all query from that orders table, but they only care about a specific store. If they're querying by store ID, all of a sudden we can't really prune that table very well because it's not well clustered on that column. So instead, we can use the automatic clustering service. This is provided by Snowflake as a kind of fully serverless and managed solution for changing the clustering of a table to match a specific column or a couple of columns that you need. So you can enable this, and Snowflake will just, in the background, delete and recreate those micro-partitions to cluster them against the key that you specify. The downside is that it comes at a cost. So whenever you use the automatic clustering service, it's really important to both monitor the performance of the queries which are hitting the table, but also the cost of running that automatic clustering service as well to decide if it's worth it. And then finally, we have this manual sorting option. So in the same way that naturally clustered tables really are just sorted by the clustered column, we can do that ourselves manually. So if you run a create or replace table as a select from that very same table ordered by the column that you want to cluster by, Snowflake is just going to replace that table with a sorted version of itself, which leaves you kind of in the same state as the natural clustering that I mentioned before. So if you have a table which is either static or like rarely updated, this is the most cost-effective way to get to a well-clustered state. The downside of manual sorting is that if any DML operations occur to the table while you're performing this create or replace operation, you can actually lose those DML operations as Snowflake replaces it at the end of the query. So this is really only for places where a table is not being updated. So how do we find good candidates for clustering? Really, it just comes down to columns which are used in where clauses and also join conditions, which Ian will mention in a bit. But the column should have a large enough number of distinct values that Snowflake is able to discard columns that aren't needed. So if you choose a column which has only got 2 different values, like a true or a false, and they represent maybe like 50% of the values in the table each, and you filter on that, Snowflake at most is going to be able to discard half the micro-partitions. If instead you use something like a timestamp that we mentioned before, you'll see much better pruning performance because Snowflake can discard more micro-partitions. And you can use query history, access history, as well as just your kind of own understanding and knowledge of the data to understand what a good column is to cluster by. Okay, let's go to query design.
Sweet, thank you. Yeah, so Niall's laid down some good foundations on how to structure your tables in a way that you can achieve pruning, and then how you can achieve the different methods you can use to cluster. What I want to talk about next is, once you've done all that, what are different ways you can design your queries to ensure they're running efficiently. Before I do that, I want to share 2 things that I'd want everyone to consider before they go down this route. So the first is understanding what the expected ROI is. The last thing we want is for practitioners to go spend hours or days tuning queries or changing configurations if the payback won't be there for the business. So that's an important thing to understand up front. Make sure whatever optimization effort you're embarking on is going to provide the value relative to the time you'll spend. The next thing when it comes to queries is seeing if you can reduce the frequency. So a common thing that we see is you may have a dashboard that contains a bunch of queries. That dashboard is scheduled to run every hour, and then correspondingly, the data models that populate that table are also scheduled to run every hour. That can add up, so it's worth scrutinizing. Are people actually looking at this every hour? Doesn't need to be run that frequently. When you look at the cost side of that, you can save a lot of money just by changing the frequency. So if you think about a data model that costs $10,000 a year because it's updating every hour, just by switching that to run once per day, you can drop up to 95% of those costs. Cool. Let's move on to some of the things you can do once you've checked those boxes on how you can actually make your queries run faster. So if there's one tip I want everyone to remember from today, which applies to any modern data warehouse, is this old database adage, which says the fastest way to process data is to not process data. So we spent a lot of time talking about query pruning and clustering for this exact reason. The Snowflake optimizer does an amazing job of taking the different filters you put in your query and then figuring out which micropartitions actually need to be read. So we showed an example earlier where we selected from we filtered on an order date with a constant. Snowflake handles that great. They also will handle more complex scenarios where you calculate a value you want to filter on through a CT or a subquery. So most of the time this just works, but there are certain scenarios where it can fail. Some examples of that are if you apply a function on the predicate in your filter, or if you do a type conversion. Another interesting thing that can happen is your table can get degraded clustering health. So those micropartitions don't have a narrow range of data anymore. An example of where that can happen is like I'm wearing a Whoop band, so this emits event data. I don't know if Whoop is using Snowflake, but it emits data up into some data warehouse. So normally that data arrives the day it's emitted, but there could be scenarios where my device goes offline for a week and then it comes back on. And now all of a sudden we have all of this old data being mixed with new data. And that could hurt your clustering health because those micropartitions now have a mix of old and new data. So whenever you have a query that's taking a long time to run or it's expensive, it's worth taking a look at the query profile that Niall showed or the query history to make sure that you're getting the pruning you expect, because there are those scenarios where it may not be optimal. The other recommendation to process less data is to use incremental materializations. So in today's age, it's very common for people to do data transformations in the warehouse. Because it's easy, a common pattern is just to create a data model that just reprocesses all the data every time it runs. Most of the time, this is fine, but for larger data sets, that can get really expensive. So we encourage, for those more complex models, you consider incremental materializations where you only process the new records that haven't been processed yet and don't kind of waste all that compute reprocessing the same data over and over. The next tip is about another way in which you can enable pruning in Snowflake, which is a really interesting one. So the examples we showed before are something that's called static pruning. So when Niall showed that example on the orders table where you had a where order date greater than date, that's something Snowflake can figure out upfront in the cloud services layer when it's deciding what micro-partitions need to be read for your query. Another way you can do this is through an optimization Snowflake has built in called join filtering. And what happens here is when you have two tables, Snowflake can look at the values in one of the tables and then use that to push down to the other table to decide, oh, these values are in this table. We actually only need these certain micro-partitions from this other table. So a good example of where this applies is in merges. So again, let's imagine we have a big orders table that maybe has billions of records. We have a small subset of those orders that we want to update. This orders table has a random unique key, we'll call it order key, and the table is not clustered by this key because it's random. So if I were to write this merge statement just using that order key, when we go to update that table, Snowflake would do a full table scan because it has to search all the micro-partitions across those billions of records to find those orders that we want to update. But we may know that we have this other column called order date that the table is well clustered by, maybe because of that natural clustering that Niall described. So if we just add in an additional join predicate on that well-clustered column, that can actually enable pruning because of that phenomenon I described where it can say, oh, what are all the order dates in this small orders temp table? Let's remove all the micro-partitions from that big table, which doesn't contain any of those dates. So this is a really important one. Whenever you have joins, and if you have a well-clustered column that's not in that join condition, and it doesn't affect the output, it's great to add those in, and you'll get much better results. The next thing I want to talk about is CTEs, which is always a hot topic in the optimization space. So we talked about query pruning before, which essentially gets rid of micro-partitions that you don't need to read. Column pruning is a similar thing. The end goal is to read less data. This time, column pruning is removing unnecessary columns that we don't need to read from a particular micro-partition. So if we look at the example I have on the bottom left, I have this CTE called active users, where I'm selecting all the columns from this user's model. If I reference that CTE later and I only select two columns, the Snowflake optimizer will recognize that and it will only read two of the columns from that table. So it'll avoid scanning potentially hundreds of other columns we don't need. So that's what column pruning is. Most of the time, this works, but there can be scenarios where this breaks down. So two examples of that are if the CTE is referenced more than once, or if the CTE is used in a join. So because of that, we recommend, just as a general practice, always explicitly list out the columns when you're defining a CTE, so you can assure you're always getting that column pruning optimization. And the last one I want to talk about is filtering early. So again, the Snowflake optimizer, most of the time, does a great job of figuring out the most efficient way to execute your query. And one of those things it does is with filter operations. So if you have a where statement at the end of your query, and that can be moved up as early as possible in the operation, Snowflake will do that automatically for you. But sometimes it can't do this. So an example is this query on the right, where we have a couple joins, and then we have a qualify statement at the very end. This qualify statement will actually run after all that expensive join has been done against those data sets, and then we may end up discarding half the records. So if you look closely, this qualify statement actually just operates on one of the tables. So the most effective way to write this query would actually be to push that up into a CTE before the joins, where you filter out all those rows on that table using that same qualify statement. And then when the joins happen, they're working on much less data, which will make your query faster. So whenever possible, help Snowflake out. Make your filters as early as possible so you can avoid processing as much data. Great. As we wrap up, we want to leave you with some final suggestions and resources. So if you're looking to get started with better understanding your Snowflake usage, we've open sourced a package that called dbt Snowflake Monitoring that helps you understand cost drivers. And one of the most useful things it does, which Niall hinted at earlier, is we have a query cost attribution model in there. So you can use that to identify within a virtual warehouse what are the most expensive queries or workloads that are driving my costs, and where should I focus my time. From there, you can create dashboards to monitor your costs, notify your team if there's a big spike, and then create lightweight rituals like a monthly or quarterly review to keep tabs on your costs and decide, hey, maybe we should spend a bit of time this sprint optimizing one of these workloads. And then the last thing I want to call out is that for anyone looking to immediately lower their Snowflake costs or better understand their spend, we do have a SaaS product that's currently available in early access. So if anyone's interested, happy to chat more about that. It does a lot of the things we talked about today. So yeah, feel free to chat with us at any point, or you can send us an email, hello@slack.dev. We'd love to talk. And with that, yeah, I just want to say thanks so much for listening.